We're going to be looking at graphing trig functions, specifically sine and cosine graphs. So in class, we would have gone through some exploration stuff, and really just the only thing I want to touch on is just kind of identifying some of the features here. So again, this is your general sinusoidal graph right here, and of course you've got your midline, which is going to be the distance between your crests and your troughs, divided by 2. So for instance, our troughs are these bottom like vertices here, and our crests are these top vertices. And the distance between them, cut in half, is going to be your midline. We also describe the amplitude as the distance from a trough to a midline or from a crest to a midline. It's always expressed as a positive value, so it's like the absolute value. So even though you're going down from your midline to a trough, it's still the amplitude is still described as being positive, even if the entire curve itself is in the negative side. Your amplitude is always a positive value. And so the other thing that just sort of arises from this is, in general, the domain for these functions are always just any real number. And the range will be basically from your trough to your crest. Okay, whatever the y values of the trough to the y values of the crest. And of course, this is just like, as soon as we have a word problem, there are some context. Of course, there can be additional restrictions. But just in general, with a generic function, it's going to be x is real, and then your y is restricted crest to trough. And of course, y is real. So let's actually get down to business and start graphing some stuff. So when we are talking about general features and you're asked to identify things, here's the things that you could be asked to identify. Of course, domain and range always with any function, y-intercept, and then our x-intercepts. Now, the purpose of this page is just kind of talk about those intercepts there. So let's start with y-intercept, because y-intercept is always nice and easy. For any function, when you have a y-intercept, you just want to make x equal to 0. So I want to make x equal to 0, which is basically me saying g of 0 in this case is equal to 2 cos of 0 minus 1. And this is where it's important to just kind of reflect on the earlier trig stuff we did. And you have to think about, okay, cosine of 0, I'm either going to use especially if you don't have a calculator, I should say, you're going to either use one of your special angles or just your kind of your unit circle, that generic graph that you have there of like your zeros, your 90s, your 270s, all your multiples of 90s essentially. So I see 0 degrees is definitely my multiple of 90, or a multiple of pi over 2 if we're dealing in radians. And so I'm going to think to myself, okay, on my graph, on my unit circle there, when I have 0 degrees, what's going to be my cosine value? And remember that little trick I taught you where your cosines are like your coasts. So your coasts are 1 or -1 at 0 and at pi here. So as soon as I see 0 degrees, I can replace that 2 cos of 0 with 2 times 1 minus 1. And then, of course, g of 0 then would be 2 minus 1, or just 1. Okay, so we have a y-intercept at 0, 1. Let's look at our x-intercepts. X-intercepts can be a little bit spicier. And so some of you probably have already made the connection here that when you're looking at a graph like this, there are many x-intercepts possible. And of course, if the graph is translated so far up or down, or has a very small amplitude, it's possible to have no x-intercept. So it's either kind of an all or nothing, and that's all or nothing in the truest sense of the word. As soon as you're going to have at least one x-intercept, you're going to have all the x-intercepts. You will have an infinite number of x-intercepts in either direction, which means, of course, we're going to have to express that using some sort of general notation. So let's just follow this through here and see if this one does have all those x-intercepts. So to find x-intercepts, you're going to make y is equal to 0, and 0 is equal to 2 cos of x minus 1. So I'll add 1 and divide by 2 to either side. Cos of x is equal to 1/2. And in this case, if you don't have a calculator, this fraction that pops out has to be some fraction or some multiple of a special angle, okay? You always want to reduce it down too, right? Because if I got 4 over 8, I don't have a special triangle with a side of 4 and a side of 8. But if I reduce it down, I definitely have one with 1 and 2. So again, I'm just going to do a quick sketch of a special triangle right here, because I know I've got a triangle that's 1, 2, root 3, and across from the root 3 is the pi over 3. So the only way to get a cosine of 1/2 is with pi over 3. So that tells me then that if I actually show like all my steps here, I do the inverse of 1/2, and that gives me x, that's going to give me pi over 3. But it's not just pi over 3. It's going to be all the multiples of pi over 3. It's also going to be the quadrants, the other quadrants that have a positive cosine value. So if you think for a second here, back to our days of trigonometry before we were graphing, Pi over 3 is in this quadrant. Cosine is also positive down in this quadrant, which is actually going to give us 5 pi over 3. So in terms of values, it's going to be pi over 3 and 5 pi over 3 for sure. And then you have to remember that, you're going to have an infinite number of coterminal angles because you can go all the way around and get another angle, go all the way around and get another angle. And that's going in the negative direction. We could also go in the positive direction and go all the way around and get an angle. Sorry, I should have started here. Go all the way around and get an angle. Go all the way around and get an angle. So we've got to communicate this through some notation here. So you have an x-intercept either at, and I'll do this in piecewise notation here. So it's going to be pi over 3 plus 2 pi n, where n is an integer. And you also have 5 pi over 3 plus 2 pi n is an integer. And I'll just use this notation. These are my x-intercepts. So either your x-intercepts are coming from pi thirds plus 2 pi n, because remember this is communicating like these. This is like coterminal, right? So coterminal, it's going all the way around and landing in the exact same spot. And we're using n here just to represent that, hey, it just has to be a multiple, but it has to be a whole number that's either positive or negative. So you can put in -5 or 5 or 17 or -138, but you can't put in a number like pi, right? Because you have to go the whole way around. You have to go a full 2 pi around. You can't go some portion of 2 pi because it has to land in the exact same spot. So when you're looking at this is how you express your x-intercepts. So you can break it up, of course, and say x-intercepts is this, comma, is that. And that's how you express them, right? You have an infinite number. Now, if you ever get to a point, in this case, let me see if I can just highlight this. When you're isolating for cosine or sine, you end up with a number that's greater than 1 or less than -1, then there's actually going to be no solutions, and you can stop right there. So for instance, if I ever got to a point where I had cos of x was equal to 1.7, or cos of x was equal to negative 2.2 or something, there's no way for that to happen, because if you think to your basic sine and cosine graphs, as we're going to get into, they're always oscillating between 1 and -1. So there's no way for them to go outside those bounds when you isolate for that. So as soon as you get a number bigger than 1 or a number less than -1, you can just stop and say there's going to be no x-intercepts or no solution, because you could be finding something other than an x-intercept, right? But yeah, so there's going to be no solution if you get down to that right there. And of course, this holds true for sine as well and sine as well. Yeah, so let's actually go and start graphing these. I'm kind of like stealing a bit of my thunder later on, but so our general form, or the standard way that these are expressed, of course, just using that standard way of just showing all the different transformations that have taken place, nice and clearly labeled, with A being our vertical stretch, B being our horizontal stretch, C being a horizontal translation, and D being a vertical translation. Now these manifest themselves in an interesting way, where this is our amplitude. This is and B is also special. B is like how many wavelengths in 2 pi. Okay, so for instance, when B is just 1, you get 1 wavelength in 2 pi. When B is 2, you get 2 wavelengths in 2 pi. When B is 1/4, you would only get 1/4 of a wavelength in 2 pi. Okay, and then C and D, those manifest themselves depending on whether we're talking about cosine or sine, and we'll get into that in a second here. And is there anything else I want to be... Oh, and just always, in pre-calculus here, we're always going to be in radians. Realistically, that's the default. There's only, in physics, sometimes you'll do questions like this where it's expressed in degrees, but in our class, always going to be in radians. And finally, when it comes to sine and cosine, the one little trick that I like telling students is every pi over 2, something is happening, okay? So like when I mean that something, it's either going to be a midline. It's kind of like a little pattern. Here you go. Midline, crest, midline, trough, rinse and repeat. Okay. Midline, crest, midline, trough, midline, crest, midline, trough. And so the distance between these things is pi over 2, unless you have a stretch going on. And whatever that stretch is, you just literally divide it out of the pi over 2. So for instance, in this case, the sine of 1/2 of x. So I would say, okay, every pi over 2 something's happening, but I also have this stretch. So I'm going to divide out that stretch. So pi over 2 divided by 1/2. Well, pi over 2 divided by 1/2, I'll just multiply the reciprocal, but multiply by 2 over 1. These cancel. So now every pi something happens. It doesn't change its pattern, midline crest, midline trough, midline crest, midline trough. It just means in that particular case, instead of it happening every pi over 2, it's happening every pi. Okay, so let's look at this right here. So you've got a sine function, and I see, all right, pi over 2 is my magic number. Every pi over 2 something happens. However, I've got that pesky 3 there, so I'm going to divide out that 3, which means that it'll be every pi over 6 something is happening. So I'm going to zoom in right here. And by the way, I don't have anything else going on. My amplitude, I don't see a number there, so the amplitude is just 1. And I don't see a vertical translation, so I'm just staying at the original midline of 0. So my midline here is going to be 0. I've got an amplitude of 1, which means it's going to go no higher than up to 1 and no lower than down to -1. And then I know that sine starts, I'm putting that in kind of a quotation marks right here, but 0, 0 is one of my anchor points for sine. Because if you think to your unit circle and what sine is doing at 0, when your input is 0, sine outputs to 0. So every pi over 6, something's happening. So here I started a midline, I go another pi over 6, it's a crest. I go another pi over 6, it's a trough. Go another pi over 6, it's midline, another pi over 6, that's a trough, and then another pi over 6, I have a midline. Another pi over 6, I have a crest. I'm going to say this right one time. You go another pi over 6, midline, go another pi over 6, trough. So I've got something that looks like this. You look at this bad boy right here, and of course it just oscillates forever, right? Like there's no, doesn't end. By the way, I'm able to do that so quickly because I see that one of these units equals to pi over 6. So even though they might be expressing it, they might have simplified the fraction like pi over 2 or -2 pi over 3 or whatever, I know that this distance represents pi over 6. So that's how I'm able to just keep on following that pattern. So there, you can see it clearly drawn out there. If I was asked to do a domain, I'd say x is real, and then my range would be from -1 to 1, and then y is real. And that's how I would write that out. Or I could use interval notation. I could say -1 to 1, and then y is an element of that. And when you use interval notation, it's assumed to be in the real number system. You can kind of see here the work I had done in class here, so let me just erase this, and we'll start fresh right here. So f of x is 2 sine x plus 1. So again, sine normally, now I'm going to draw kind of my anchor point for sine is 0, 0, but I can see it's been moved up 1. So this has been literally moved up 1, and that point is now there. So I'm going to erase this junk. And that's my midline, right? And like this number at the end, by the way, I should have mentioned that earlier, is always going to be my midline when it comes to sine and cos. And I can see here I've got an amplitude of 2, so I'm going to go up 2 from that point. So it's never going to go above 3, and it'll never go below -2. Okay, and I don't see a multiplier there, which means every pi over 2 something's happening. Okay, so every pi over 2, so I have a midline, and then did I go down? This looks wonky here. I think I went too far down here. I'm starting at 1, down 2 is to -1, so boy, there we go. That looks better. So now I'm going to go every pi over 2, something's happening. So I'm going to find pi over 2 here. Here's pi over 2. And by the way, this is a positive number there. So I know that I'm going to be opening up, and pi over 2 takes me to this point here. Another pi over 2 takes me to pi, which will take me back to the midline. Another pi over 2 takes me to 3 pi over 2, which takes me down to a trough. So again, something that looks like this. And it'll open back up to my midline here, which is approximately right there. And of course, pi over 2 takes me down to here to a new trough. And then that repeats. Okay? Just looking at this right here, it looks like these x-intercepts aren't nice numbers, so you couldn't really solve for them without... oh, look, no, sorry, you know what? I'm misspeaking here, because look, I can just tell that sine of x equals to -1/2. That's going to be one of our special triangles right there. So I can do sine inverse of x, sine inverse of 1/2, -1/2. That gives me pi over 6, I believe. Let me draw my special triangle just to make sense, just make sure. 1, 2, √3. And then down here would be the pi over 6, yeah. So pi over 6, except it's not going to be pi over 6. Pi over 6 is our reference angle. So I have to think where sine is negative, and sine's negative down here. So in this quadrant or that quadrant. So what would that be? So 6 pi, so this would be 7 pi over 6 or 11 pi over 6. And you can actually see it, right? Like when I'm looking at this, my graph's a little bit off here. So this should be looking more like this, but 7 pi over 6 is where it crosses. And of course, there's an infinite number of them. So I would go 7 pi over 6 plus 2 pi n is an integer, ditto for the 11 pi over 6. So just the exact same thing there again. I just want to do a cosine briefly here. So cos is a little bit different. So before my anchor point was 0, 0. With cosine, it's 0, 1. And you can just remind yourself, okay, when I plug 0 into my cos function, cos of 0 is equal to 1. I see that I have been moved up 2. So I'm going to move this up 2. And that takes me to 2 there. And I can see that I've been shifted over pi thirds to the right. So I'm just going to go here and I'm going to move this pi thirds to the right. So this point is now here. Okay, so I've been shifted up and shifted over, and cosine starts like cosine looks. A cosine graph and a sine graph are indistinguishable. It just depends on how you want to describe that curve. Do you describe it with sine or cosine? So a cosine graph starts at the top, where so you might be wondering, do I have to go one up from this point? And the answer is no, because a cosine starts at a crest. So this is my crest right here. This is a crest. And I'm still going to follow that rule where every pi over 2 something happens. Now, the one tricky thing about this is I have to add pi over 2 to pi thirds. So let's just, or actually, the easier way is for me just to look at what does pi over 2 represent. You could add the fractions, but when I'm looking at this right here, I can see that 1, 2, 3 squares or 3 grids is going to represent pi over 2. So from this point then, I'm just going to go 1, 2, 3 and put a midline. 1, 2, 3. I'm going to put a trough. 1, 2, 3. Put another midline. And I can subtract 3. 1, 2, 3. I'm going to put a midline. 1, 2, 3. Put a trough. And to kind of sketch this out, I'll get something that looks like that. Okay. And again, if you were ever in a void asked to find x-intercepts, so you could say, hey, cos of x minus pi thirds is equal to -2, because you would have moved the 2 over. That's impossible, okay? Because it goes outside that and 1 to -1. And that's basically it for sketching these graphs right here. There's a challenge version down here that you can check the notes for and compare with. And yeah, so that's it for this video. I will see you guys in the next one.